That the integral of ln x raised to the nth power dx, they say that is equal to fn of x. So this is fn of x. All right, fn of x. So that's it, that's fn of x. This is fn of x. And so if you're integrating ln x to the n dx, what do? When you integrate this, what you're going to get is the integral of, you can rewrite ln x to the n as 1 times ln x to the n. And you might say, why did I put that 1 there? That 1 comes there because we're going to be able to use by parts by putting the 1 there, dx. Then now, when you have the 1 right here, you can remember by parts, you have to use the Eyelids Rule. So let me write down Eyelid. And what does Eyelid Rule tell us? It tells us that we substitute for u, logs come before algebra. And so we're going to substitute u as ln x to the n. And so du is going to be equal to, we carry down the power n, we subtract 1 from the power to get ln x to the n minus 1. Then you multiply it by the derivative of ln x, which is 1 over x. So it's really all of this over x. That's du. Then dv is equal to 1. And when we integrate 1, we get v is equal to x. So now we can continue now and say then that fn of x is actually going to be equal to, using by parts, it's uv minus the integral of v du. uv minus the integral of v du. So it's going to be equal to u times v and u times v, that's going to be x ln x raised to the n minus the integral of v du. Minus the integral of v du. Now x times this, the x is going to cancel each other. And then I'm going to factor out the n to have the integral of ln x to the n minus 1. dx. If you're wondering what happened to the x, let me put it in another color. Right here, you remember it's being divided by x. And then here it's being multiplied by x. But these two x will cancel each other in reality. All right? So what this works out to be then, it is just x ln x raised to the n minus n times, now the integral of ln x to the n minus 1, that's just fn minus 1 of x. That's how we do this question. Easily shown, soft. All right, nice and easy, soft. So we can write shown easily. Shown, too easy. Now it says hence or otherwise, show that f32 minus f31 is that right there. So that fnx, f32 minus f31 is that thing right there. So to do that, You have to start by writing down back that fnx is equal to x times, it is x times ln x to the n. Nice, it's x times ln x to the n minus n f n minus 1 of x. Nice. Now that we need to prove this, what are we going to do? Well, first thing I like to do is start by finding what is f3 of x. So to find what is f3 of x, we can substitute n as 3. So f3 of x will be equal to x ln x to the third power minus 3 times f2x, because 3 minus 1 is 2. 3 times f2x. Cool. All right, and so what we're getting is x ln x cube minus 3 times f2x. And what is f2x? Well, f2x is we're going to replace again and with 2 now. So f2x is x times ln x square minus 2 times, replace with 2, it becomes 2 minus 1, which is f1 of x. All right, so before it looks any more complicated, I'm going to simplify what this is. So it's working out to be x ln x ln x ln x cube minus 3x ln x square, and then expanding, minus and minus become plus, it's become plus 6 times f1x. Now all we need to do is find out what is f1x. So let's do it, let's get it. Finding out what is f1x, it's going to work out to be x times ln x cube minus 3x ln x square plus 6 times f1, and that's going to be 6 times f1 of x. It's going to be replaced with 1, and it's going to be x times ln x. So it's x ln x minus 1 times f naught of x. Now f naught of x, to find what is f naught of x, we have to go back and remember that f naught of x, when n is 0, ln x to the 0, anything to the 0 is 1, and so the integral of 1 is x. And so we can actually just replace this f naught x with just x. This is really x ln x minus x. And so this is the formula now for f3x. Good. Now that we have the formula for f3x, we can now evaluate what is f3 of 2 minus f3 of 1. All we're going to do is replace x with 2 and 1. So it's going to be f3 of 2, replacing x with 2. We're going to get 2 times ln x cube. Just want to make sure we make no mistake. minus 3 times 2 is 6, so you get 6 times ln 2 square plus 6 times, in quotation or in open brackets, 2 ln 2 ln 2 minus 2, close up that bracket, minus, now we're going to put in 1, but guys, we know that ln 1 is 0, so this is 0, this is 0, this is 0, this is 0, and so it works out to be 6 times minus 1, it just works out to be, in bracket, 6 times minus 1, because everything else is 0, ln of 1 is 0. So all of this is going to work out to be 2 ln x cube minus 6 times ln 2 square plus, now 6 times 2 ln 2, that is going to be 6 times 2 is 12, so it's 12 ln 2 minus 6 times 2 is minus 12. Then this looks like minus 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 minus, that becomes plus, so it's become plus 6. So finally the final answer is just going to be 2 ln x cube, 2 ln x cube minus 6 times ln 2 square, 6 times ln 2 square plus 12 ln 2 then minus 12 plus 6 is just minus 6. Is that what they have? Let me check it. All right. Yes, that's what they have. That's what the question wanted us to prove. So finally, that's it. So we complete the proof. We can write soft. All right. So yes, that's it. Now part B now is partial fraction. All right. And integration. All right. So let's look at that. So this is the proof. So we complete it. So you can write soft. Nice. Part B. Part B is partial fraction, and in doing this partial fraction in part B, we have y squared plus 2y plus 1, and that's being divided by y to the 4 plus 2y squared plus 1. That's the question that we have. So first and foremost, we just need to know that, well, I can rewrite this as, this is really y squared plus 2y plus 1 divided by, I can rewrite the denominator as y squared plus 1 all squared. I can rewrite this denominator because this is a perfect square. All right. Then by partial fraction, I know I can separate it as ay plus b over y squared plus 1 all squared plus cy plus b over y squared plus 1. I can separate it like that. So that is exactly what we're going to do. So to do that separation now, I don't know why the line came out like that. That wasn't how I intended it to be. wanted a straight line. Let's give me a straight line. So finding the LCM now, yeah, this is it. So the LCM with these two is going to be, of course, y squared plus 1 all square. And this into this just leaves ay plus b. Then plus all of a sudden the writing is so much smaller. Then this into this is going to leave cy plus d being multiplied by y squared plus 1. And all of this is, of course, equal to this over here. So it's equal to your y squared plus 2y plus 1 over your y to the 4 plus 2y squared plus 1. Now, what did we learn in primary school? We learned in primary and preparatory school that whenever the denominator are the same, we equate the numerators. So we're going to equate the numerators, so that implies that equating numerators, y squared plus 2y plus 1, that's going to be equal to ay plus b plus, now if I were to expand this, I would get cy times y squared, which is plus cy squared, plus cy times 1 is plus cy, plus dy squared, plus d. Nice and easy. Now, what we can do now is equate coefficients. Notice that we have cy times y to give us cy cubed, not cy squared, cy cubed. Cy times y squared is cy cubed, cy times 1 is cy, d times y squared is dy squared, d times 1 is d. Notice right here that we have a cy cubed, and there's no y cubed term over here, and so c must equal 0. C must be 0. All right? And let's go to blue now. We have a y squared here, and we have dy squared here. And so the coefficient of this is 1, and so d must equal 1. All right? D must equal 1. Now that we get that d equal 1, let me see. All right, so we need to find a and we need to find b. Let's equate now y terms. Equating y terms, we have 2y here, and we have ay plus cy. So what that is telling us then is that 2 is equal to a plus c. But c is 0. Remember, c is 0. And so c is 0. And so since c is equal to 0, it tells us that a must be 2. A equal 2. Nice. So now we'll find a. Finally, let's go ahead now and find out our constant. We have 1 here is equal to b plus d. So 1 is equal to b plus d. But we already know what is d. D is 1. And so b must equal 0. So b must be equal to 0. Because 1 is equal to b plus d. All right, now that we get that, then we can replace these now. So just for shortening, I can't bother to write out all of this again. Let me call all of this fraction I, right? I'm calling the fraction I. So therefore, the fraction I is equal to AY plus B. AY plus B, what is Y? AY, A is 2, so it's equal to AY, which is 2Y over Y squared plus 1 all square all right, plus CY plus D. C is 0, so it's D now. D is 1 over Y squared plus 1. Nice and easy. Soft. And this is it, so prove it. Remember, addition is commutative, so you can refix the order to give them what they had. Nice. Then it says, hence, evaluate an integral. So hence, so part 2 says hence evaluate the integral from 0 to 1 of y squared plus 2y plus 1. Hence, evaluate the integral of y squared plus 2y plus 1 over y to the 4 plus 2y squared plus 1 dy. Hence, evaluate this integral. So to evaluate this integral, what we're going to get is that this is actually equal to the integral from 0 to 1 of, we just showed that y squared plus 2y plus 1 over that was the same as 1 over y squared plus 1. So it's going to be the integral of this dy plus the integral from 0 to 1 of 2y over y squared plus 1 all square. So let's go ahead and knock out these integration. Now to do this integration, 1 over y squared plus 1, when you integrate that, it's going to be tan inverse of y. This is just tan inverse of y from 0 to 1. Tan inverse of y from 0 to 1. Plus, now right here now, let's do the rest, this integration here. Now if we were to call u, let's call u y squared. If we were to call u y squared plus 1, right here, if we were to call this u is y squared plus 1, then I would realize that du would be 2y dy. All right, so what I'm going to do then is I'm going to rewrite this as the integral from 0 to 1 of 1. And then I'd have to change the limits of the integral because I'm saying that u is y squared plus 1. So when y is 0, then the lower limit becomes 1. And when y is 1, upper limit becomes 2. So it's now the integral from 1 to 2 of 2y dy is du, so it becomes 1 over, this becomes y squared plus 1 is u, it becomes 1 over u squared du, and I'm integrating from 1 to 2 using substitution. Plugging in 1, I get tan inverse of 1. So I get tan inverse of 1 minus tan inverse of 0, which is minus 0, plus, when I'm doing this integration now, it becomes, this is really u to the minus 2, so I add 1 to the power to get u to the minus 1, divide by the power of minus 1, and of course I'm integrating from 1 to 2. integrating from 1 to 2. So let's go ahead and do that. Tan inverse of 1 is, I don't know, so I put it in my calculator. Tan inverse of 1, that looks like pi by 4. That's pi by 4. Plus, we put in 2 and 1 now. When we put in 2, we have 2 to the minus 1. 2 raised to the minus 1 divided by minus 1 is minus a half. When we plug in 2 here, 2 to the minus 1 divided by minus 1. That's minus a half. Minus, when we put in 1 here, it's going to be 1 raised to the minus 1 divided by minus 1. 1 raised to the minus 1 divided by minus 1 is just minus 1, so it becomes minus a half plus 1. Minus a half plus 1 is just minus a half plus 1 is just a half. So the final answer is just pi by 4 plus a half. Nice and easy, that's the answer. Just to be safe, let's check it. Just to be safe, we're just checking it right here. All right, just being safe. Plug in back 2 again, 2 to the minus 1 over minus 1. Minus 1 to the minus 1 is 1 divided by minus 1. Yes, it's a half, so this is right. So that takes care of module 1. Let's go to module 2. Module 2 question